Hi students, welcome back to the class. So far we have learned about vector algebra. Of course we learned about what are vectors, types of vectors and the addition of vectors, and in the last class we learned about components of vectors. So we learned that a vector have three components, namely I cap, j cap, z cap in the respective directions of x axis, y axis and z axis, and hence we are able to locate any point or any vector in the three-dimensional plane, right? So in this class we are going to define the next operation. So far we have defined vector addition, subtraction, etc. so that we can find the negative of a vector a plus b, a minus b. Of course we learned the properties of vector addition and so on. So in this class we are going to discuss about the multiplication. Of course we know that multiplication is one of the most important property or most important operation in all the arithmetic, as well as in mathematics, as well as in other branches of science. Multiplication is one of the inevitable operation, right? So in this class we are going to define vector multiplication. So vector multiplication, we know that we can always multiply two numbers in one and only one way, that is the multiplication of two numbers. But when it comes to functions, we know that we can find the point-wise product of the functions as well as the composition of two functions. Similarly, we have two kinds of product when it comes to the case of vectors. The first one is dot product. So dot product is one of the type of vector multiplications we are going to evaluate the product of two vectors. So there are two types of vector multiplication, dot product as well as cross product. The first one is dot product, or we also name this product as scalar product of two vectors. So dot product or scalar product of two vectors is nothing but whenever we are given with two vectors a and v, the dot product is denoted by vector a dot vector b. See, here we marked a dot, that's why we say that this is dot product, and it is defined as modulus of vector a into modulus of vector b into cos theta, where theta is the angle between vector A and vector B. So we define vector A dot B as mod A dot mod B cos theta, and theta is nothing but the angle between. Suppose we are provided with two vectors, vector A and vector B, like this, then theta, the angle between these two vectors is nothing but this. See, if we are provided with two vectors in a random position, we can take this vector and place it here so that we can find a theta here also. So the dot product of two vectors is nothing but mod A mod B cos theta, and theta is the angle between A and B, and we have a restriction 0 less than or equal to theta less than or equal to pi. Since after a complete rotation the angle again keeps on repeating, we get a repeated angle which is exactly same as theta. So what we are taking is only the variation of theta from 0 to pi. So this is the definition of dot product of any two vectors. Now we shall move on to some observation regarding this dot product. So we have already defined a dot b is nothing but mod a dot mod b cos theta, where theta is the angle between the two vectors as well as 0 less than or equal to theta less than or equal to pi. Now on the basis of this we shall have some observations. These observations are very important, so just watch it very carefully. First observation, vector A equal to 0, if vector A equal to 0 or vector B equal to 0. We know that if vector A or vector B equal to 0, we can never define the angle between these two vectors because one vector is 0. So in that case we define A dot B as nothing but A dot B is equal to 0. If either of the vectors is equal to 0, we define the dot product as equal to 0. Always remember that if whenever one vector is equal to 0, then the dot product is nothing but 0. Okay, always this is similar to the case when it comes to the multiplication of numbers. 0 into any number is nothing but 0. Similar is the case when One of the vectors is 0, 0 into another vector is definitely 0. Clear? Now, vector A and vector B be two non-zero vectors. Then, A dot B equal to 0 if and only if vector A perpendicular to vector B. Why? Because we defined A dot B as mod A mod B cos theta. When A dot B, when A and B are perpendicular vectors, then definitely theta will become 90 degree. Right? Perpendicular implies theta is equal to 90 degree. We know that cos 90 degree is nothing but 0. So the definition becomes mod A mod B 0 into 0, which means this quantity becomes nothing but 0. So we get theta equal to when the vectors are perpendicular. Perpendicular implies dot product is 0. Conversely, 0 implies these two vectors must be perpendicular. These are the only options for the dot product to be 0. So always remember that whenever any of the vector is 0, then the scalar product or dot product is definitely 0. Also, whenever the two vectors are perpendicular, then also the dot product is nothing but 0. Now the third property, if theta is equal to 0, which means that the two vectors lie in a same line or parallel line, which means that the two vectors are nothing but collinear vectors. So if the vectors are collinear or theta is equal to 0, A dot B is nothing but mod A mod B, because cos 0 is nothing but 1. Right? So we get mod A mod B is equal to A dot B. Similarly, we can say that A dot A is nothing but A and A are collinear vectors. Since they are lies on same line, so we get A dot A is nothing but mod A into mod A, which is mod A square. I hope this is very clear. Now the fourth point is, if theta is equal to pi, now you can say if theta is equal to pi, cos pi is nothing but, yes, cos pi is nothing but minus 1. So the definition become A dot B is equal to mod A mod B into minus 1. So we have minus mod A mod B. Similarly, A dot minus A. We know that whenever we are provided with a vector A, minus A is nothing but the same vector in a reversed direction. So the angle between them is pi. So we get A dot minus A is nothing but minus mod A into mod A, which is equal to minus mod A square. So I hope this is also clear. Now the next observation is nothing but, this is a very interesting observation in this entire chapter. We know that I cap, j cap, k cap are the unit vectors in the respective axis, x-axis, y-axis and z-axis. Also we know that x-axis and y-axis are perpendicular to each other, right? Y-axis and z-axis are perpendicular to each other. So I cap in dot j cap, the angle between them is I dot j is 90 degree. So whenever the angle between them is 90 degree, dot product equal to 0. Similarly, j cap dot k cap. Similarly, k cap dot I cap. Also note that whenever two vectors are parallel or collinear, we have I dot I. The angle between them is nothing but 0 degree. So I dot I is nothing but mod I square, right? Now note that I is a unit vector, right? So, and the magnitude of a unit vector is nothing but 1. So it will become 1 square equal to 1. So I dot I cap dot I cap is nothing but 1. Similarly, j cap dot j cap and k cap dot k cap, because the magnitude of the unit vectors are nothing but 1. Okay, now the third point, angle between two non-zero vectors. See, from here we have cos theta is nothing but A dot B by mod A mod B. That is this formula. Cos theta is nothing but A dot B by mod A mod B. Very important formula for all your exams. So cos theta is nothing but A dot B by mod A mod B. And by using the inverse trigonometric formula, we have theta is nothing but cos inverse of this. Right? Very simple. And the last observation is the scalar product is commutative, because A dot B is nothing but B dot A. A dot B is equal to mod A mod B cos theta. B dot A is equal to mod B mod A cos theta, which are same. Because the angle between them is never changing, and mod A into mod B is same as that of mod A mod B into mod A. So the scalar product is commutative. Note that we call the dot product as scalar product also, because mod A is a scalar or a real number. Mod B is of course a scalar. Cos theta is a scalar. So when we multiply these things together, we get a scalar, which means that whenever we are multiplying the two vectors in dot product formula, we always get a scalar. So that we call a dot product is also as a scalar product. Clear? Now we shall move to the next section. Now we shall move to the most handy calculation in finding dot product. So far we have learned that A dot B is nothing but mod A into mod B cos theta. But it is not always possible for us to find theta in between these two vectors. Suppose that I have a vector like this and I have a vector like this, and I am not able to find the angle between them always. Is it possible? So we should have a more handy trick to do this, right? So in that case, let me define vector A as nothing but a1 I cap plus a2 j cap plus a3 k cap. I am able to do so because we have already said that always it is possible to represent any vector in this component form, right, with the three components. And also let me represent vector B as like b1 I cap plus b2 j cap plus b3 k cap, right? Now I am going to find the dot product. Let A dot B is nothing but this vector dot this vector, right? So we have a1 I cap plus a2 j cap plus a3 k cap dot b1 I cap plus b2 j cap plus p3 k cap, isn't it? Okay, now I am going to multiply or open this bracket just in the case of arithmetic multiplication. Let me show how. A1 into this is equal to a1 I cap into b1 I cap plus b2 j cap plus b3 k cap. This is the first component, plus a2 j cap into, first I have multiplied this with this entire sum and then this with this entire sum, b1 I cap plus b2 j cap plus b3 k cap. This derivation is very important since I have seen so many exams. In so many exams this derivation itself has asked directly. So let's listen very carefully and understand. Then the third component plus a3 k cap into b1 I cap plus b2 j cap plus b3 k cap, right? I just opened the bracket. Now again I can open this bracket by multiplying each with each. Then a1 I cap into b1 I cap is equal to a1 I cap into b1 I cap. Sorry, a1 I cap dot. Here we are finding the dot product plus a1 I cap into, sorry, dot again. I am making the same mistake again and again. b2 j cap again plus a1 I cap dot b3 k cap plus a2 j cap dot b1 I cap plus a2 j cap dot b2 j cap plus a2 j cap dot b3 k cap. Again we have a3 k cap dot b1 I cap plus a3 k cap dot b2 j cap plus a3 k cap dot b3 k cap. See, I have just opened each and every bracket, right? Now observe that we have already said that whenever I am provided with two numbers and a scalar in a vector product, I am able to associate them, right? Here I am associating them as equal to a1 dot b1, let it be there, I dot I, which is I square. I square is nothing, mod I square is nothing but 1. We have already proved that in the observation sections. I dot I is nothing but mod I into mod I cos 0, because they are collinear. Also 0 is nothing but, cos 0 is nothing but 1. It will result in I square, so it will become I square, mod I square, which is nothing but 1. So it is nothing but a1 b1 plus a1 b2 into I dot j cap. We have already proved that I dot j cap is nothing but 0. So this product becomes 0. Similarly, this product I dot k cap also becomes 0. Now, a2 j cap dot b1 I cap. J cap dot I cap is again 0. a2 j cap dot b2 j cap. See, j cap dot j cap is nothing but mod j square equal to 1. So it is equal to a2 b2 into 1. So we have a2 b2. Then again, a2 j cap b3 k cap equal to 0. a3 k cap b1 I cap equal to again 0. And a3 k cap b2 j cap again 0. Last, a3 k cap into b3 k cap, it is equal to a3 b3 because k cap square is nothing but 1. So we get, whenever I am provided with two vectors a and b, we can express them in the component form. So a dot b is nothing but a1 b1 plus a2 b2 plus a3 b3. So simple. We are no need to find the angle between them. Just evaluate the corresponding products and find the sum. So always remember this result because we are going to do lots and lots of problems using this definition. Now students, listen. Suppose L is a directed line. Suppose that L is a directed line, which means that we can prolong this line until the end of the plane. So this is L is a directed line, just a directed line. And suppose that this is a vector and I name this vector as AB. So this is the vector AB. Now the projection of the vector AB on the directed line L is nothing but the vector which comes like this. That is, when we form a triangle like this, the base of the triangle which lies in the directed line is called the projection. Projection of the vector AB in the directed line L. So the projection of the vector AB in the directed line L is nothing but the base of the triangle which is formed, right triangle which is formed like this. Clear? So this is nothing but AC is the projection of the vector AB. Also note that this is the vector AB. So this is magnitude of AB. This distance is the magnitude of AB. And suppose this is cos theta, then magnitude of the vector AC or the magnitude of the projection is nothing but modulus of AB into cos theta. We know this by trigonometric ratios. Cos theta is nothing but adjacent side into hypotenuse for any right angle triangle. So we get mod AC is equal to mod AB into cos theta. This is the projection of a vector on a directed line. And the direction of the vector or the direction of the projection of the vector changes according to the sign of the cos theta. Let me explain how. Suppose that we know that in a coordinate plane system or in the quadrant system, here we have all the trigonometric ratios are positive. Here we have sine and its reciprocal are positive. Here tan and its reciprocal are positive. Here cos and its reciprocal are positive. So when the vector lies here or when the vector lies here, cos theta is positive. And when the vector lies here and here, cos theta is nothing but negative. So when I choose a vector like this, the direction of the projection will be like this. Now suppose that I have a vector like this and this is our directed line segment, and then we know that the projection is nothing but it lies here, right? This is the projection and this is the vector AB. This is the projection and the direction of AC is nothing like here because here cos theta is negative, so we chooses the direction in the negative direction. Similarly, suppose that suppose that this is my directed line segment and suppose that the vector AB like this, vector AB lies like this and this is cos theta. Clearly cos theta is negative in the third quadrant, so the direction of the projection is from here to here, A to C, and suppose that it is my directed line segment and I got a vector like this. Since it is in the fourth quadrant, cos theta is positive, so the direction of the projection is from here to here. So it is easier for you to choose the direction of the projection, because the direction of the projection is very important when it comes to your competitive exam. Now we shall move to the properties of this projection of a vector. Now we shall move to the some observations regarding projection of a vector. Recall that we already said that whenever we are given with a vector and a directed line, the projection means we are considering this vector onto this directed line, so we get a vector here. This is the projection of the, this means the projection of the vector AB, and the magnitude of this can be evaluated by, this is theta, so modulus of AB cos theta by trigonometric right angle formula. So let it be there. Now first question, first observation, if p cap is the unit vector along a line L, then the projection of a vector a bar on the line L is given by a bar p cap. Of course that's true, because this is the directed line L and this is the vector A. Now suppose that p cap is the unit vector along this direction, then a bar dot p cap is nothing but a vector here. This is the nothing but a bar dot p cap from here to here, because p cap is a unit vector, and when we multiply it with a bar, we get a vector in the direction of this directed line segment, as well as the magnitude will be modulus of a bar dot p cap equal to nothing but a cos theta, since mod p is nothing but 1, because it is a unit vector. This is the condition required for a vector to be a projection. Magnitude should be a cos theta. This is satisfied. So whenever we are given with p cap, which is the unit vector in the directed line segment, then the projection is nothing but a bar into p cap. Now the next property, projection of a vector a bar on the other vector b bar is given by a bar b cap. So suppose that instead of a line segment here, we are given with a vector b bar and this is vector a bar. Similarly, we can project this same vector here to the vector b bar just by taking b cap here and multiplying it with the a bar, just as in the first case. So projection of a vector in the direction of a vector b bar is nothing but a bar into b cap. Simple, isn't it? Now we shall move to the third observation. If theta equal to 0, then the projection vector of AB will be AB itself. Theta equal to 0 means if we are given with a vector and the vector itself projects onto itself, that means theta equal to 0. So the projection of the vector AB projected onto itself is nothing but AB itself. Clear? If theta equal to 0, the projection will be AB itself. If theta is equal to pi, which means that we have to project a vector. Suppose that this is our vector AB and this is the directed line segment and this is the vector AB. We want to project this AB onto the directed line segment like this. Then if theta equal to pi, then the projection of the vector AB will be minus AB. Minus AB is nothing but BA, because AB should be projected onto this line segment, which means that we have to transform this line to here. So AB will become BA. The projection will become in this direction and this direction is nothing but BA. This is AB and we are projecting the line segment onto the line segment. So the initial point comes to the terminal point and terminal point comes to the initial point, or the direction gets reversed, which means that the projection of AB when theta is equal to pi is nothing but BA. Always remember this. The projection of AB when theta is equal to pi is nothing but BA. Now we shall move to the next observation. If theta is equal to pi by 2 or 3 pi by 2, then the projection vector of AB will be 0 vector, because we know that whenever a vector is given and a directed line segment is given, the magnitude should be a cos theta. When theta is equal to 90 degree or pi by 2 or 3 pi by 2, a cos theta will become 0, since cos pi by 2 and cos 3 pi by 2 are 0. So the magnitude will become 0, which is possible only for the 0 vector. So we have, if theta equal to pi by 2 or 3 pi by 2, then the projection vector of AB will be the 0 vector. So these 4 points regarding the projection vectors are to be kept in mind. So in order to solve problems, we are going to apply these results. So now I hope that you have understood these concepts we have discussed in this class. Further topics will be discussed in the coming classes or coming sessions. So wait for it, stay tuned and watch this video well to have a better understanding of the coming classes. Thank you.